Okay, good morning. Welcome to the Colloquium series. Today our speaker is Professor Prasant Mohapatra from University of California, Davis. His title of his presentation is Mobile Video Quality and Smartphone Application Profiling. Before he gives the presentation, I would like to say a few words about Professor Mohapatra. He is currently a Tim Booker Family Endowed Chair Professor at Department of Computer Sciences at the University of California, Davis. He was also the department chair for the last 6 years at least, and still is. He has also held visiting scientist positions at Intel Corporation, Panasonic Technologies, Institute for Infocom Research in Singapore, and National ICT Australia, as well as visiting professorships at University of Padua, Italy, KAIST Korea, and also Yonsei University, South Korea. He is and he was on several editorial boards, including Transaction on Mobile Computing, Transaction on Parallel and Distributed Computing, ACM-YNet, and ad hoc networks. He has chaired and has been on the program or organizational as well as steering committees for several of the top conferences, including Infocom and Mobicom. He is a fellow of IEEE. He has received doctoral degree from Penn State University in 1993 and received Outstanding Engineering Alumni Award in 2008. He has also received Outstanding Engineering Faculty Award from UC Davis and HP Lab Innovation Award. Professor Mohapatra's research interests are in the area of wireless and mobile networks, security, quality of service experience in both wired and wireless networks. His research has been funded through grants from several prestigious organizations, but we in the community know him as one of the magnets for bringing young people together, and I have had the chance for a long time to see how students, also how other junior faculty have worked very well with him. He is one of the main leaders of a large initiative on the network science that he doesn't say much about. With this, Professor Mohapatra.
Many thanks, and that introduction was too generous. I hope I keep the talk up to that level. It's my pleasure to be over here, and this is my first visit to, well, I've come to UW a few times earlier, but this is my first opportunity to give a talk over here. So during the next hour, I'll give you a glimpse of two of our work related to mobile networking. So we'll talk about mobile video quality and smartphone app profiling. The two parts are kind of interrelated. The first part we'll talk about the kind of the quality of videos in your iPhones, Android phones, and so on. And the second part will move more into the apps. Before we get into that, here is a kind of a laundry list of some of the other projects that I'm involved in. We do work on context-aware communications, physical and cross-layer assisted network security, trusted networks. This is the network science project that Radha just mentioned about. We are also looking at smart network analytics, and all our smartphone work comes under these categories. And I'm new into the area of forensics. The video quality work that I'll talk about, that falls under this mobile video expeditions, and these are the two topics that I'll talk more over here. This is another project, the Quell Ridge, which I'm very passionate about, and unfortunately I won't have time to talk about that. So this is about a large wide area outdoor test bed that we have built in Napa Valley, which has been operational for the last 5 years and has been very useful in many of our research activities, and it has been truly a passion for me. So again, wireless is very ubiquitous. As we all know, there are several applications, smart grid, healthcare, supply chain tracking, broadband accesses, road safety, and many other applications that are evolving. And as you know, along with those evolution, we are also getting the devices downsized, okay? So gone are the days, very The frequency of time that you see desktops are kind of diminishing slowly. Probably, you know, laptop will give their way to smartphones and so on. And no, I recently did some, you know, empirical study on myself that I found that, you know, I'm spending more time on my iPhone compared to my laptop. So, you know, things are changing. The devices are becoming smaller, and as we go on, we will see more of those changes. So, coming on to the first part of the talk about quality of video, let me give a little bit motivation. Before that, the first part, the video quality work, was published in Mobicom this year, and the second part will be a paper which will be appear in another venue in a month or two. So, if you look at all the predictions, like Cisco predicted, or Cisco found out that 50% of the traffic are related to video traffic in mobile networks in 2011, and the prediction is by 2014 this number will go up to 70%. Okay? And as a result of which, evaluation of video quality is becoming increasingly important. It's not only for we as users, it's also very important for network service providers like AT&T, Verizon, and so on. And so the problem over here in video quality is like, how do I say, you know, if I'm watching YouTube over here, you have your Android device, how do I say my video is better than your video? It's not that easy to say, you know, compared to what we were doing in wired networks, mainly because accessing video quality, especially in mobile devices, is hard. And I'll clarify that further, why it is harder than the normal video quality evaluation, and also you have to make it more meaningful in a way to do it. If I'm watching a video over here in YouTube, my service provider is AT&T. If the quality drops, AT&T needs to know right away. Nowadays, in the current standard, they won't know about it. There's no point for me to do the evaluation and tell them that, okay, the quality of video was poor. That will be too late for them. And again, if I want to find out or if I want to measure the quality of video, it has to be quick, and you should be able to do in devices which have very limited capabilities, both in terms of processing power, batteries, and you know, other type of interfaces. So, if you let me start with an example. What you see over here is in snapshot A. This is the same picture. In snapshot, it's the same picture of an old lady sitting in front of a post office. So, in snapshot A, you see one picture. Snapshot B, you see one picture. We have a lot of people over here. We can take a poll over here to find out, okay, which one is better. And if I ask you to give a rating between 1 and 5, I hope you won't disagree with me if the left one gets a rating of 4 to 5 and the right one will get a lower rating, okay, because that's not clear. Now, what I just explained is actually a subjective video quality metric. So, subjective video quality metric are measured in terms of what is called as a MOS score, mean opinion score, which ranges from 1 to 5. It's evaluated by human viewers, so the cost is very high. I cannot afford to do these kind of measurements on my smartphones. I don't want to, I mean, to do that is effectively you pass it around, everybody sees, scores it, you send it back to the service provider. It doesn't work that way, okay? So, we have to look at objective video metrics that are evaluated automatically by computer programs. And these, the goal, the best measure as it is agreed upon is the MOS score. So, can we come up with objective measures that resemble as close as possible to this objective score? That is the goal. Now, the problem with the existing metrics are as follows. If you look at the matrices that have been proposed, the most popular one is PSNR. So, peak signal to noise ratio, which calculates the difference. So, you have the original frame, you get a frame, you compare the difference between these two frames, and the difference will translate to the PSNR. Okay? So, that is an objective measure. Higher the PSNR value, peak signal to noise ratio, the better is the video quality. This metric has been used forever. It's quite useful. It has been very useful in wired networks. However, in wireless networks, there is a problem with it. Now, if you look at the picture over here, a car moving on a highway, okay, 100 dB is a hypothetical number, but let's say this is the original video, and I have two videos over there. you can clearly see that the quality of this video is much lower than this video, right? However, if you do the PSNR calculation and define the look at the PSNR number and define the quality, what the PSNR says is the quality of this video is better than the middle one, which is wrong. And these are actual experimental results that I'm showing. So we published a paper a few years back and showing that how PSNR is ineffective in wireless networks. So the first question is, why does it happen so? I'll give you a quick feel of the reason why this happens. PSNR, the way it happens is you get the original frame you get encode it and send it over, and then at the receiving side you have the original frame and compare the received frame, corresponding frames one by one, and you try to find the difference and compute the PSNR value. It works well in wired networks because the losses are extremely rare in wired networks. In wireless networks, the losses are not as rare as in wired networks, the result of which, when you have some losses, then the comparison becomes misaligned over here. Okay? So similar things happen, as a result of which most frame by frame comparison, when they get misaligned, that essentially results in PSNR computation like this, which does not correspond to the quality of video that you see on the screen. Okay? That's one major problem, and the other major problem is for PSNR calculation, you need the original video. Just think about it. You are downloading. Nowadays, we get videos from sources that we don't know even where they came from, because you download something from YouTube, you may not know who uploaded it, where it got uploaded, and so on. So if you don't have the original frame, you cannot do a PSNR computation. For evaluating mobile video quality, the characteristics that we need is it need to have low computational requirement. It should be independent of the video codec. In today's world, there are so many video codecs. You don't want to develop metrics that say that, okay, if you are using video codec A, this is the metric, video codec B, this is another metric, and so you don't want to have that. And another goal is, do we really need the video quality just to define the quality of experience by the user? Okay? That itself will be an accomplishment, but can we use it further? So what we are trying to see is, if the quality is changing from that metric, can we give some feedback to the AT&Ts of the world saying that, hey, there is something wrong, you need to tune this knob or that knob? Can we provide that kind of information? That is another goal. Again, we cannot, like PSNR type of metric, which requires the original videos. Let's assume that we have no reference videos. The complete reference model is too much of an overload. And also, the goal is how close we can get to the MOS score. That's a subjective measure. Okay? So there are two ways you can measure the quality: spatial quality assessment or temporal quality. Spatial quality, if it gets messed up, you will have blocking and blurring. While you are watching, you will see blocking and blurring of videos. And you can do pixel by pixel comparison. So PSNR will capture those. Structural similarity, SSIM will capture that. In temporal quality assessment, the impact of temporal quality, if it is messed up, is jerkiness and freezing of the frames. Optical flows are like, basically, if there is a movement, if I am moving my hand like this, you know, the accurate tracking of my hand movement is the best one, is the optical flow, is how you look at it. So the goal is, when you transfer the video, you should have a smooth flow like that. So temporal quality assessment will be more important in mobile networks, and I'll explain as we go along why. So our approach is, again, we want to find out an objective video quality. The overall goal is it should be very close to the subjective matrices, like the MOS score. What we have introduced in this work is a new metric called temporal variation metric. I'll refer that as TVM. Using that, we derive temporal variation index, TVI, and I'll elaborate on both of these things. And that is our main contribution in this work, which is a reduced reference video quality metric. it estimates, it has two goals. It estimates the subjective score pretty accurately or pretty closely, and the other thing is it also provides, it can also provide real-time feedback to the carriers in order to say what kind of impairment may be happening in the network. Okay? So, let's look at the main idea behind this metric. In that, what we are introducing is, as I said, is a temporal variation metric. So, the idea is as follows, is the distance between two neighboring frames. Don't get confused with PSNR. It might sound like PSNR, but it's different than PSNR. In PSNR, you have the original frame and the received frame. You are comparing that. Here, what I'm doing is I'm comparing consecutive frame, P, P plus 1, then P plus 1, P plus 2, and so on. So, if I take frame P minus 1 and P, P minus 1 and P, if I do a comparison of that and find the difference between these two neighbor frames, okay, and we derive an expression out of it where K basically captures the the depth of the images in there and all. So, there are fine tuning that have been captured by these equations, but let me talk to you about the main essence of the idea is we capture, let's say this object moved from here to here. So, this is the difference of that. So, we take difference of consecutive frames, okay, and use that in deriving our metric. Now, in terms of difference, I could take the temporal variation of the structural similarities. So, all these are, this is the edge similarity, this is the visual signal to noise ratio. I can take all these matrices and can take the difference of consecutive frames also. Okay? In fact, we did that to see what makes sense and what doesn't. Okay? So, if these are all the existing metrics. I can take these matrices from one frame, find the corresponding matrix in the next frame, take the difference and do that. So, I can come up with all these things. I have just added T before all of these things, and let's see how the results will look like. All the work that I am showing today are all experimental results. Okay? So, we took a set of videos. Some of the videos are out there, very popularly used by researchers in this area. Some we generated on our own, but the goal was to have slow moving, fast moving, medium moving type of videos and different resolutions. So, what we observed is, if you look at, so this the first plot that you see, this is the frame numbers as they increase, and we have a kind of normalized value of the variations that you see of these matrices that we talked about. Now, this is the optical flow. So, this is what we want to achieve, this kind of trend. And these are all different kinds. I don't know whether you can read it from there. The green one is TSSIM, the red one is TVSNR, and so on. So, we wanted to see how this, for example, if you see the green one is not tracking the pink one very well, whereas the blue one is tracking a lot better, the red one is tracking to some extent, and actually the quantification of the numbers are presented over here. So, what we see from this result is, our goal is we can make any of these differences as a metric. We wanted to see which one will be better than the others. Okay? So, from this study, we could see that, so here is the correlations, TVM is better, TVSNR is better, TSS is not good, and so on. So, this is like what tracks the optical variation closely. The next graph that you see is the running time, how much of computational overhead they have. Yes?
Optical flow, is that a metric that has its own derivation? Are you trying to match optical flow?
We are trying to match. Okay? We use that as the best case. It's kind of offline measured. That is the best case. That if as I said, if my hand is moving, if you have a perfectly good video of that. Okay? So, that's like the best case. We are putting that as the standard.
Its own metric. And
right.
You can,
yeah.
Okay, gotcha.
Now, so here we plot the computational time taken. Here we find out the memory requirement. By looking at these three things, so we have a choice of all these 4 different types of metrics that we talked about earlier. We found out that TVM is better in terms of tracking the optical flow, lower computational needs and lower storage needs. And lower computational and storage needs are required for these kind of devices. Okay? So, to elaborate that further, so what we did is, we want to now using TVM, okay, temporal variation metric, we use that in order to find TVI. So, TVI is nothing but we take the TVM of the original video. So, when the video is being sent, let's say YouTube video is being sent, what you do is you compute the TVM. So, all the corresponding consecutive frames, the differences of that, you just compute that, and these are just numbers. The overhead is actually in terms of kilobytes only, so it's not very high. So, what you do that, you send your video, you send this in an out of band channel. There's very little overhead in that. At the receiving side, what you do is you compute the TVM locally. Okay, what I received is I compute. Remember, this sounds very much like, internet transmission. When you have parity bits, it's more or less like that. So, you compute it at the receiving end. Receiving end, you compute a TVM. So, let's call that TVM R. The difference of this will give you this new index TVI. So, I have kind of normalized that over the original one. So, basically, the proportion of difference that you see in TVM, that gives you the TVI. Okay? So, and we ran this through a lot of experiments. Actually, I ran it through some real data that I work very, very closely with AT&T, and we ran with some real data that you observe with your cell phone. I cannot show you this data because of my contractual obligation, but we had other experiments. The results I'll show you of that. So, basically, we developed an Android app, and we engaged 17 volunteers. That's the number of PhD students I have. So, so we collected 50 video clips and formed 3 groups, and wanted to find the MOS score. And so, basically, the goal is find the MOS score and then use our approach to calculate the TVM and then the TVI. Okay. So, the quality of experience that we see is there was a strong correlation with the Pearson coefficient. Pearson coefficient is the term that is used to define the MOS score. However close we get to that is better. Okay? So, we found that there is a strong linear correlation. I always tend to show 3 graphs. The main the reason is, one is we have sampled about 50 videos. We have classified into fast motion, slow motion, and medium motion of the videos. Okay? So, in all the cases, the correlation ranged from 0.87 to 0.96 with the MOS score. We also wanted to check. Remember, I made 2 promises to begin with, that we want to provide an useful metric to quantify the quality of experience for the user. So, that's on the user side. The other thing is, can we use, if I am watching some video over here, unless AT&T knows that I'm getting blocking or blurring or whatever, they don't know anything why is the quality getting impacted. Unless they know, they cannot turn some knobs at their end to fix it, right? So, the other goal that I promised earlier is, can we provide some feedback to these carriers or the service provider in order to react, or in order to have the information of what is degrading the quality of experience of the videos. So, in order to do that, we set up some .11n nodes and created a test bed, and we have again 3 motion groups is again fast moving, slow moving, medium moving. So, we wanted to introduce packet losses and delay separately, one at a time, and wanted to see what is the corresponding impact or TVI. So, the goal is, can we look at the TVI and TVM to get some unique signature? If I am looking at that, so let's say so to give you a realistic example, and we have done this also and worked with AT&T for that, is if I am getting these pictures, if this carrier is viewing this, can they see that, okay, if this is how the graph is looking at, I am having network delays rather than packet losses. If this is happening, there are probably packet losses. Okay? So, those kind of granularity that we are looking at, can we get some instant feedback? So, here we ran about 183 video samples in order to get some of the results. So, let me give you a flavor of what we are looking at. Again, we have done quite a bit of detailed study of this, and if you look up our paper in Mobicom this year, you'll get more results in that. So first thing is, let's say if the carrier can find out by looking at this graph that the packet losses. Remember, packet losses causes blocking, blurring, and freezing. Okay. So first thing what you see is in this graph, the green one is actually the original TVM. The green curve that you see is the original TVM. Okay. Then what we did is artificially we created packet loss ratio of 0.5%, and that is the blue line, and the red line is the 3% packet loss. So very high packet loss in the red line. So you can see that as soon as you introduce packet losses, the TVM, what you would see without any of the losses, the difference is quite high. It's not that they look alike anymore that you can say you cannot detect it. So it's completely, you can see that, like, let's say the green is going over here, blue is going over here and all. And sometimes you can see, if you look at the red one, then you can see maybe it is falling behind a little bit, and there are a few things that I will blow up. You can see that there is a gap over here. There might be more gaps at other places. If you look carefully, you'll find that. What these things help us is in defining unique signatures in order to give a hint back to the carrier on what is causing the quality degradation. As an user, I will say, okay, the video quality is not good. But as carrier, I need to know what do you mean by not good? Is it blocking or freezing, or why it could be happening, and all those things. So let me expand that up in a little bit. So as I said, packet losses cause blocking and blurring. Now, if you expand upon, this is the previous one, I have blown up a few frames, you can see that there are gaps in over here, there are gaps in over here. Gap means what? When we are doing a comparison with respect to, if you remember the expression, I'm finding the original TVM, subtracting the received TVM. If both of them are identical, then if I don't get the original one, then the denominator becomes 0, so the result is infinite. That's where there are this missing point. So missing point basically tells that if they're looking at the graph, they will tell that, okay, there is freezing at the other end. There is blocking happening at the other end. So blocking is due to packet loss. So they will know that there is something happening in their network because of which there are packet losses. How they resolve it, that's not the scope of this, but at least you give them the feedback that there is packet losses. Okay. Similarly, if the carrier service, we have also, I'll kind of skip this part, we have also come up with ways by using TVM and TVI, how you can estimate the packet loss rate. So let's say this TVI and TVM is given, we are giving instant feedback from our smartphones at the TVI values. Can my carrier AT&T figure out that, okay, they will figure out, okay, there is packet loss is happening. Can they estimate from the TVI value? That was our goal, and we have shown that you can have very close estimation in all different kinds of video of the packet loss rate by just looking at the TVI. Okay. Same thing, I want to expand that to delays. So delays results in freezing. If you don't have your frame, you have a frozen frame, you keep on watching that until, and this happens quite frequently, right? And that is very annoying. So in case of end-to-end delay, when the end-to-end delay increases, if you look at this, so here the blue one is the original TVM, okay? And in the red one that you see is delayed by 3 seconds. What you can see over here is because of the delay, so this is the TVM value, because of the delays, the TVM values sometimes become infinite, so that's why there are no red points in this region. Okay? The other thing that you can notice that the red one is actually shifted, kind of a shift to the right of the blue curve. Okay? So these gives you unique signature that if you are looking at this graph as a carrier engineer, you will say that this is not, there is no probably packet loss, this is happening due to delay. Okay? And we have also expanded that how you can estimate the delay if you are getting the TVI index. Okay, so yes.
So infinite values because the denominator is 0.
Right.
And you said TBI, the denominator is the cent value of TB.
Right. In this case, you didn't get anything, so you're putting the default as 0. You didn't get anything, so it's just infinite. You just don't count it.
Oh, so you're not taking the actual value from
Right.
the cent thing.
Yeah.
You're saying.
Because you didn't get, so you don't know the actual value.
Oh, I got it. This is
Right.
on the smartphone.
Right. It's on the smartphone. Yeah.
Gotcha, okay.
Yeah.
But
So
where you are getting it, they may be offset in time and otherwise fairly similar.
I'll show you that. That's a good point. So that's in the next one. So what is actually happening is, so because of this delay, let's say this is the period which is delay. So basically F3, F4, F5, F6, they arrived consecutively, but they were delayed. They were kind of shift over there. Now, if you look at it, so basically when you get this F4, F5, F6 later, since we are comparing the consecutive frames, their TVM is still good because they are still consecutive. But the thing is, because you had this gap, everything is shifted now. So those kind of information, the carrier can easily figure out that even if the TVI value was good in that case, because you missed a few frames, your network is incurring delays. Okay, so you can turn some knobs on to do whatever if you can in order to do this. So the overall goal is, so that there are two takeaway messages from this part of the study. First of all, this was, again, I didn't have enough time to give you a survey of what is being used, but first when I started working at AT&T, I spent about 1 day per week over there. I found that the metric that they are currently using is very, very trivial. So these type of metric will be very useful for service provider, especially for smartphone applications. And the other thing, the second part that I talked about is how we can use the metric. One goal was to provide a higher quality of experience. The other goal is, can I use the same metric as a service provider in order to identify which knob should I turn when at my end in order to improve your QoE? Okay. So the concluding remarks of this part is, I already mentioned all this. TVI can measure the temporal information at a very low cost. And again, all the results that I showed are actual implementation. And we derive TBI as a quality for users and a predictor of network conditions for the service provider. Okay? And we have shown through analyzing several videos that is highly correlated with MOS score. Okay? MOS score is considered as kind of the bar that you want to achieve. Okay? So again, I've showed you examples of how you can detect packet losses as well as delays, but again, it could be used for other type of network metrics, and we are exploring some parts of it. Any questions before I switch gear to the next part? Yes.
Looks like in order to compute the TVM, you need to have the motion compensated difference. How do you measure that part of? Because from one frame to the other frame, in order to do the difference, you need to know the motion part. Otherwise, you cannot detect the difference.
Right. So we have. So the question is, how do we measure the difference? So let's say the original video is movement of my hand, and you have 2 frames back to back that are showing, one position like this, the other position like this. So we have used a simplified metric, and the details of that we have in the paper. I didn't have a slide on that. We have used a very simplified metric just to come up with numbers in order to quantify these differences. Okay, so this is not exactly the complete difference. We took some points and then found the difference, and then they have used, and we have shown that, okay, if you do fine tuning by knowing the content of the video, whether it is slow, medium, or fast, you can do much better improvement in there. We haven't done that yet, but even without that, the correlation is quite high. But as you see, the correlation we are getting in 92, but you can jack up that correlation if you find a better way of quantifying the differences. We have used a very simplistic approach. Okay. Yes.
I know in 802.11 the packets are acknowledged, but I don't know about the 3G or 4G transmission. Does the infrastructure have any other way of detecting packet loss more directly, and possibly without so much cooperation from the instrument from the receiver?
That's a good question. So the question is, will the service provider or the carrier find this information out in a different way, which will not require the feedback from the user device? The answer is yes and no. And we had, I mean, this is a question for which we probably had days of discussion at AT&T. So the problem with that is, and it's a very interesting question, the problem with that is, at the end of the day, what matters is what the user sees on the screen. So ideally, the carrier wants a feedback right what is happening on the screen onto their end, okay? The other thing is, yes, the carrier has control over something, but if I'm viewing a video over here, if my access point over here in this department is messed up, okay, AT&T has no control over that. They will never get any information from this last hop. Similarly, think about the first hop. There is some server uploading the video. AT&T has no control over that. So there are many parts over there in the flow of data from the source to the user over which the network doesn't have any control over. So in this case also, you can say that if you are providing that information, that it is that you have a lot of delays, but if the delay is happening at your last hop, what the carrier can do? They cannot do anything probably, but at least they will know whether they can identify whether the problem is with their base station just prior to this hop, or it is happening in your own local network. So all this information, it's much better to get the feedback directly from the user device rather than anywhere in between, because what matters is the user experience at the end. So that's a very challenging question. There's no clear solution, but this is one, based on my discussion with them, they think that irrespective of what is happening where, it's much better for the service provider to get the feedback from the experience of the users. Yes?
You mentioned that with the feedback they would turn down knobs. What kind of knobs would you suggest?
Okay, so I was trying to avoid that because that's not the scope in there. So basically, again, this relates to the previous question. If I am AT&T, I don't have any control over your last hop or what is the original quality of video and so on. All the control that I have is I can change, let's say, the transmission power of my base station, or I can schedule some traffic, move from one base station to another, or I can use higher uplink versus downlink, or increase my core network and all those are my controls over there. If I'm seeing continuously that there is a lot of delay in this part of the network, then probably I can turn some knobs in order to fix that. If there are some losses in this type of network, maybe I have to upgrade something or allocate more resources to that part. So this will give you a first cut of what kind of resource allocation you need to do in order to do that. So in other words, we provide this tool to AT&T, then the next step is if I knew what knobs AT&T had, I could do a corresponding mapping of what knobs need to be turned to this. So right now, we have generalized it that we are providing feedback whether you are having packet loss or delays, and we are trying to also provide feedback on throughput and all that thing. Okay. Other questions? Yes.
So this TVM is extracting a statistic, I guess, from frames. And does it distinguish between, for example, maintaining high resolution but losing frames, and, for example, not losing frames but losing information within each frame, so kind of noise? Like the picture of the lady in the park, there's a lot of blur, just lost pixels,
right.
But maybe it's still moving smoothly. And do you see distinctions between that situation and one where it's all clear but you're missing frames?
We will capture actually both, and the goal is to provide a matrix to that if there are frames missing. So one way to say it is how close you are into the original video. If you miss a few frames from the original, that will get captured in TVI. Okay. If the original video is blurry, if you get a blurry, our TVI will be still high because it is very close to the original. Okay. So the goal is to quantify the quality in terms of the temporal variation. There are some instances that we have seen that you miss because if there is very spatial. So let's say you have a video of a constant picture in there. That's where our metric won't perform that well.
Because it's not temporal change, it's
Exactly.
just noise, basically.
Yes.
Okay, gotcha.
Okay, so let me move on to the next part, which is quite interesting, and I've enjoyed working on this. Is we all use several apps on our phones and all. There are several free apps, and they're always popular. I have a teenage son, so I know how popular these are. The question that we wanted to ask is, are free apps really free? Okay, so just to give you some starting point, in April 2010, at an average, there were about 22 apps per Android phone and 47 apps in iPhones. So this number has been increasing significantly and would be quite different, at least 2 to 3 times right now. In December of last year, about 10 billion Android apps were downloaded, and 1 billion is increasing per month. At the same time, almost the same time, 25 billion iPhone apps were downloaded. Okay, so basically, I wanted to give you that this business is very high volume. When you have apps, app needs to be installed. You will operate those. All these consume network traffic. Okay, and smartphone generates close to 90% of the mobile traffic. Okay. So we are talking about huge volume and huge scale of things in smartphone, and very few things in the network world became popular as fast as these smartphones. So in all these apps, overhead exists. What I mean by overhead is, or before I get to overhead, is you have data traffic that is required to make your app functional. You are running an app. You need some traffic in order to make it functional. For example, you need to install it, update it. You are playing some games. The scores need to be updated. The guy you killed over there needs to lie down, and all those things need to be done. Okay, but beyond that, there are overheads that are not necessary, okay, to run the app, but they're necessary for the revenue for the app developer and all. But those overheads are basically advertisements or the analytic. Okay, so pick any free app, you will find these things are there. Now our goal is, can we quantify the impact of these overheads? Overhead, in the days when we had unlimited bandwidth services, so no, overhead was not that big a deal. However, now all services are capped. Okay, you pay for how much bandwidth you use, and also if you use too much bandwidth, your performance is reduced for the other types of apps you are running. And again, and this is a big issue for the network service providers, because they have limited bandwidth. Spectrum is the most expensive part in wireless communication, and they don't want you to use a whole lot of it. So our objective was to quantify the overheads. The way we did, and because of the time, I'll go a little faster from the initial part, and I'll focus more on the results in this part. So we built an experimental platform. We collected a lot of data by capturing the packets, and we have developed a tool to identify the overheads. So for the data collection, again, we took smartphones, and I'll show you pictures on how we have done. We have taken a lot more phones than what I have listed over here, variety of phones, did experiments all different times of days and nights and all that, and captured all possible packets. So the overall model is as follows. I'll have, we have a bunch of iPhones, Android phones. They are running apps. We have bought about 200 plus apps, and we feed that through. We have an access point that is serving those. And basically, we have a sneaky network monitor who captures all the packets in there. Okay, and then we do all our analysis. So that's the type. So the way we started is we look at 5 different categories that are more popular. Okay, I've learned this from my teenager. So, and in each of these categories, we identify top 3 apps. Actually, we have identified top 5 apps. And again, these things are much easier to do because the statistics are available out there in the internet. And we did for both free apps and paid apps. Okay. It sounds simple, but there are a lot of initial struggle we had to go through in order to make sure that the measurements are accurate. There are so many things happening in a smartphone that unless you identify what is doing what, your measurements will be wrong. So you have to clean the smartphone, clean within quotes. There are a lot of built-in apps which can be removed, cannot be removed, and all that. So we played around with a lot of OS level things. Finally, we have a quote clean unquote type of smartphone where nothing else is running. And we captured both active and inactive modes. Active means you are running the app, you are playing that game, the Angry Bird, you are shooting it or whatever. Inactive is it's running in the background. Some of the apps, for example, if you are running Facebook, they consume a whole lot of resources even if when you are not using them. Okay? So we looked at both the cases, and using that we developed a tool which we called as OHI App Overhead Identifier. So to save time, what we do in that is we capture all the packets, and we have a protocol packet filter, which basically we look at. We are capturing using Wireshark and TCP dumps, and we look at the packet filters and we identify what packet is for what. And we capture all the IP addresses that is going to. We are looking at the network traffic, and then we basically, this tool makes like this whois and what is kind of queries in order to translate all the IP addresses to some meaningful names. From that, we basically do the web host resolutions, and thereby we know, there are certain web hosts which are meant for advertisement, certain for analytics and all. So we have done a detailed classification of that. We do a lookup matching quickly in that in order to find out what is that. Yes, we might be missing a few, but not a whole lot. And so using this thing, again, I didn't go through all the details, but using this thing, we extract we kind of peel out what is the overhead packets and what are the actual packets that are being used in the app. So again, this involves also using, DNS stuff, who is search and all those things, and looking up. So for example, if I find that this is an IP address, it's going to, and this translates to this web address, so we know that this is actually Apple's mobile advertisement service. Okay, so it tells us that these are the Mobi ads that are being served. Okay, so similarly, we have identified all possible types of analytics and the advertisements in there. Most apps have separate host servers for overhead packets and data packets. Those were easier to identify, and there are some which don't distinguish, and those were hard to identify. In those cases, what we did is, in order to approximate it, we took a paid version and a free version, and the difference of that, we kind of said the extra traffic is for the advertisements. Okay, so those are the cases where we couldn't identify the host. Okay, so again, there are a lot of other fine tunings that we did that I skipped over. So let me show you some results, and the results are quite interesting. So if you look at the data, free versus paid, so if I take an iPhone which is active for 10 minutes, now in all these results I'll show you the 10 most popular app spreading over the 5 categories. If you look at an iPhone with 10 minutes of activities for all these things, you can see that the overhead in terms of kilobytes varies over this. What is almost invisible, maybe a little bit visible here, a little bit visible here, is the paid apps. Okay, how much overhead is there in the paid app versus the free apps? The blue ones are the free apps. So you can see that all I want you to infer from this graph is the overhead of the paid versions are almost negligible compared to the free version. Okay, let's go just with that for now. So this is iPhone active. This is iPhone inactive. The same trend. The other thing you might be seeing that in some cases the overheads are very high. Okay, so and these are all for iPhone active and inactive. Now, if you look at the Android, it's pretty similar. Android paid and free. The paid versions have almost negligible overheads. The free versions have quite high overhead. This is Android active for 10 minutes. This is Android inactive for 10 minutes. And you can see, like in Angry Bird, again, the scales are not the same. In Angry Bird, look at the overhead when it is inactive. It's quite high. Okay. Now, let's do some side-by-side comparison of iPhone apps versus Android apps. There is no definitive trend, But you can, so from now on, since we have realized that, okay, paid versions have very little overhead, let's ignore the paid version for now. Let's focus on free version, because remember my initial question was how expensive are free apps? So if you look at these, you can see that there is no clear trend. For example, Beat the Traffic, has very high overhead in iPhones, but almost negligible overhead in Android. Whereas if you take Angry Birds, if you are using the Android version, it has very high overhead. This is again at the active phase, whereas in iPhone it's less. Okay. Similarly, the trend, you can see all conflicting trends in different types of apps. If you look at the inactive mode, again you can see that, as I said earlier, Angry Birds has quite a bit of overhead in inactive modes, but you can see the comparison of the trends, that there is no clear trend, and in some and other thing that you see that the overheads in inactive phase are not negligible. There is quite a bit of overhead in the inactive phase also. And again, we looked at some temporal study that as you go on increasing the time, you can see that the overheads, the cumulative overhead keeps on increasing. In some cases, the growth is more towards linear. In some cases, it's kind of jumping and stabilizing and all. And again, but we saw a bit of difference in the trend when you are going through the active mode versus inactive mode. Okay? Inactive mode is either more or less constant overhead, or there are stepwise increase. Okay? Whereas in active mode, you had seen it's more or less linear type of overhead increases. Okay? Now, the same thing that we saw in Android. So these are the results for the Android ones. Now, the sources of overhead, you may not be able to read everything. As I said earlier, the way we identified the overhead is we looked at different types of sources. Some of them, these are Google Analytics server. Some of them, like DoubleClick.net, is an ad server. So once we looked at this top 10 type of apps where all they are going, we have quantified what is generating how much overhead. What we noticed that ads contributes to about 87% of the overall overhead, and most of this overhead is from third party. Third party is like MobiAd, MobiClick, those kind of things are third party ad providers. Similarly, we found that during the inactive phase, there are not much ads. In the inactive phase, about 12%, the analytics are more than the ads. So analytics are 12% more than the advertisements. And for example, forgot which one. Okay, so Andomedia, I forgot which one was that for. But you can see some of those analytics, like, okay, the second one, Google Analytics, you can see has substantial overhead. Okay, so again, if you, for example, if you are running Facebook in an inactive mode, the overhead is quite significant, and you can see that in the study of your bandwidth. So the question is, I want to wrap up quickly. I'll skip the case study. We did case studies with two most popular apps, Words with Friends and Pandora. Okay, and again, we did kind of a very fine-grained study of what is being consumed for what and all that. Again, I'll leave the slides with Radha, and you can look at this if you're more interested, or we have a published paper on this. So, but let me get to the conclusion over here. The question that I ask is, what is the real cost of free apps? So let's take an example. AT&T charges $20 for 300 megabytes. You can say, well, take $30 for 1 gigabyte or whatever. Let's not worry about the number. There is, for some amount of bandwidth, it charges some amount of money. Because these numbers are a little more favorable to me, I've used that number. So if we take $20 for 300 megabytes, if I use 1 hour per day to play games on my smartphone, okay, my son uses much more than that. So if I take that, now let me take these 4 apps, dictionary.com, Angry Birds, Fruit Ninja, and Flight View. What I've written is that the paid version costs this much. Dictionary.com cost $2.99, Angry Birds 99 cents, Fruit Ninja 99 cents, Flight View 99 cents. Okay, and I run these games for 1 hour per day for a month. The overhead in terms of megabytes that I consume are given over here. For example, in Angry Birds, I consume 200 megabytes and so on. So on the right hand side, what I want you to look at this carefully is this. If I play Angry Bird for a month, 1 hour per day, I will be paying $14 per month instead of a one-time fee of 99 cents. Okay? If I'm playing Flight View, instead of paying 99 cents, if I just get the free version, I'll be paying almost little more than $10 a month for that. Okay? The numbers could vary if you take a different plan and all, but you get the essence what I'm pointing out over here. So sometimes the cost is much, much higher in the free versions compared to the paid versions. Okay? And again, we have shown the same thing that I said, if you are using depending on whether you are using an iPhone app or Android app, the extra cost that you will be paying, and this is empirical numbers because I assumed you are paying 1 hour per month and all that, your cost you'll be paying is this much extra in a free version compared to a paid version. Okay? Okay, so with that, I will end my talk with an acknowledgement to my graduate students. I have 15 PhD students, 3 postdocs, and about 9 or 10 undergraduate students. So fairly large group of students, and I'm funded by National Science Foundation, US Army, AT&T, HP, Broadcom, Panasonic, NEC, Intel, Huawei, and a couple other startups. Okay, thank you.
Any question for Prasant?
That last analysis is very interesting and very clever. Thanks.
It was
really neat.
Yeah, so let me tell what we are trying to do next now is we did this only for bandwidth. The next thing that we want to show you, and people have looked at is the battery consumption. Because what else matters? The battery consumption, the processing power, the memory needs and all. So we have completed all that. So my goal is, for example, if you take a food item from a grocery store and the side you see a label with all the nutritional facts. My goal is to come up with a similar thing for free apps. Each free app you take, it will tell you this much extra bandwidth, this much extra battery consumption, this much extra, all the extras. You will get that information. Then you can make a decision, should I pay 99 cents or pay for these extras? Okay? Yes?
Have you looked at the signaling overhead that these sort of, I guess, free apps cause on like the LTE and UMTS protocols? Because these probably communicate in little short chunks, and that probably disturbs the cellular network.
Right, and yeah, so that's a good point. And this is, the current study that I showed where I'm looking more in terms of consumer oriented. But this is also useful for the network service provider because it adds to the extra thing. So for example, I don't know whether it's public information or not, but AT&T is contemplating, kind of the 1-800 service for apps. Is let's say if I develop an app, or you develop an app, and people see my study and say that, okay, I'm not going to get his app because it's going to consume all the battery. But if he says that, okay, he's willing to pay for the extra bandwidth, it's like 1-800 service. Whoever you are calling is paying for that call. So if that service model comes into picture, then you have the app developer or whoever is selling the app pay for the extra bandwidth. Then it will be a fairer scheme. Okay. Any other questions?
So if no other question, I also want to point out he has some of the mobile commercial products he doesn't talk about here. Let's thank the speaker again.